Well, looks like we can start. Welcome back, everyone. Well, before we get started today, I don't have a great deal of announcements, but we got through our third exam, so we're just about there towards the end. And as far as the grading is going, I should be on track for returning the exams on Wednesday's class. I'm about halfway through them. So for what we're going to do going forward, we're going to go back to section 10.5. We haven't opened it yet, but we were really leading up to it on every one of those sections, 10.1 through 10.4. We're doing tiny pieces of this full procedure finally in section 10.5. And I would say the trickiest thing about this whole procedure is actually the test statistic Z. What makes this confusing is we're used to calculating standard errors slightly differently. When we were in section 9.3, we were doing a confidence interval. And for the confidence interval, your standard error is square root of p hat times 1 minus p hat divided by the sample size n. And this gets really dangerous because for our current problems in section 10.5, we will have a p hat value. We need that, but p hat does not go here. The value we actually throw in comes directly from the null hypothesis. So I think that's a very good warm-up warning on these kinds of problems. It's really easy to get mixed up once we've seen the confidence interval procedure, and then we start learning the hypothesis test. And the highlighted in yellow, that's the nastiest spot, I'd say. Well, any questions about that at the moment? Okay, so that's where we're at so far. And if we look at the schedule, again, we'll have our third exam return on Wednesday. I should be on good track for making that happen. Then we'll have no classes at all during the Thanksgiving holiday. I wrote out an extra credit opportunity that was meant for a different class. I just put it on the wrong Moodle site. If I left it here, I'm going to modify it and correct it. I want to give a couple extra credit opportunities over the break. So if you have extra time and energy and you just want to, say, get away from the family and work on some statistics, I'll allow people to redo or submit any quiz that had gone past due. So you can do a late quiz, or if you did a quiz that you just would like to redo it for credit, you're welcome to do so. So if you have a quiz that was like a grade of 7, 8, or 9, and you just want a 10, then go for it. I'll put also a second extra credit opportunity here. And this one is really, truly extra. It's going to be a whole new statistical procedure similar to the 9.3 procedure, but I'm going to write down an extra credit opportunity where you're going to estimate not a single mean like we did right here. We can change our entire procedure and make it estimate like this. P1 minus P2, the difference between a population proportion. So that will be kind of interesting. If you're interested in working that out, the full details will be available down here, but keep in mind, it is really going to be an extra credit question in the sense that that won't be on a final exam. It won't be content we cover officially. It is now in a real sense outside of the ordinary course content. So that's what we'll be going down on the break once we get to it. We still have just 3 more days to go. Then when we come back, we'll have one normal week. Here we're finishing off chapter 12. When we come back on this week, we'll put on the finishing touches, and then we'll spend a couple days just reviewing for the final exam. Well, any questions at all, folks, about where we're at? Yeah.
Sorry, you didn't emphasize this, but when do you have the extra credit stuff turned in?
Well, I actually did not say that anywhere here, but we can say the day of the final exam would probably be a pretty natural due date. So I'll put in some of those finalized details, and let's make that our final due date. That's also going to be our final due date for WebAssign as well.
And then if we're just correcting one thing on a quiz or something, we just make the correction on the already done quiz.
Yeah, that'd be completely fine. Yeah, absolutely. Other questions at the moment? Okay, well, when we get closer to the final exam, there's going to be more and more details. The university scheduler, Michael Tin, did finally release that our exam, according to the registrar's office, and they're kind of mean people, I guess, is scheduled from 8 p.m. to 10 p.m. on Monday, December 11th. It's kind of rough. A night class on this campus usually has that time. I actually have 2 classes rolled into one. So we'll be in this room, and it'll be our class and the class that starts right after ours ends. The next class will also be in this room. It's a pretty rough time. So if that's going to be a big problem, maybe you don't study or exam well at 10 p.m. I wouldn't even know that until I've done a final exam at 10 p.m. I am also giving another final exam. I think it's at, let me double check. I'm giving a different final exam on the same day from 3 to 5 p.m. So if that just works better for your schedule, or if you feel like that's a more optimal time to actually take an exam of that kind, then just email me and we could absolutely make that happen. But officially, we'll be in this room at that time. It'll be kind of rough. We'll all get through it together. And when I write down a final exam, it's going to be 2 hours like this at a kind of a nasty time frame. I do understand that that is a tough exam to get through, and I grade it and write it with that as part of the understanding. It is going to be a comprehensive exam, but by the time we're through these weeks, you'll know exactly what's going to be on there. Well, I think it's my full spiel of announcements. Any questions or comments at the moment? Yeah. Oh, let me put that back up here. It is 3 to 5 p.m. Same day, same room, but earlier start. So by the time, if you're here from 8 to 10 p.m., I'll probably just look like I'm about ready to pass out and go to sleep, but I'll be here again at 8 to 10 p.m. Other questions so far?
Did we need to prearrange if you want to come to the earlier one?
Yeah, that'd be a good idea. Yeah, just send me a quick email and then I'll put a star on that email and they'll be all set. And keep in mind also that this is kind of a weird situation having 2 classes in one room for an exam. If you come to the earlier exam, just make sure I actually give you a statistics exam. I've made that mistake a few years ago where someone was supposed to take like a college algebra exam. I gave them a whole different class, and that's no fun to find out. And if you come in the normal time, 8 to 10 p.m., it'll be pretty clear that you're getting the wrong exam. But just let me know, hey, Mike, you screwed up. This is for something else. I need my statistics exam. I'll try to be extremely careful, but that's a terrible mistake. I just don't want to duplicate ever again. Other questions at the moment? Okay, well, let's go then to section 10.5. And here's how the notes start. I did have to make a revision on this, so apologies to anyone who printed this out early. The revision happened this morning, November 14th, and there's 2 spots. Here, I had a greater than sign. I should have said right tail test. Here I have a less than sign. I should have said left tail test. So watch the changes here in red. Sorry for all the typos in the notes so far. Those are the 2 revisions. I think what I did was it was normally called an upper tail test as per our author, and I decided to call it right tail since that's what we said earlier. But then I screwed up and called that one left tail test. So aside from those 2 those 2 revisions here and here, the notes are now complete, and here's the full procedure. This is a large sample test for a population proportion. We have to have 2 conditions, and just like with confidence intervals, the first one is about randomization, but we're at mercy to what the problem tells us. So here, we'll just mention anything we know or don't know about the sample. Some of the problems will tell us they have a random sample of certain individuals. Other problems might say we have a certain amount of individuals that are representative, but they may not be randomly selected. Other problems still don't say anything at all. So again, just like we did with confidence intervals, if you're checking those procedures, you might say the study was random. If you neglect to mention it at all, I wouldn't take off points on this, but it's something we should consider each time we go through a problem. Then, just as before, we have to carefully check this statement out. And then make a conclusion, whether the sample size is large enough or not. But already, right at this spot, this is another one of those tricky regions. What we're carefully checking is n times p naught is greater than or equal to 10, or n times 1 minus p naught. Ordinarily, if we were in the confidence interval land, this would have been n times p hat. If we have a p hat there, we're looking for the successes in the sample. But for using p naught, it came from the null hypothesis. So let's add just a little bit more description on what we're seeing right up here. This n times p naught is the expected number of successes if H naught is true. So if that's a true statement, if the population proportion is really whatever that value is specified as, then take your sample size, multiply it by what's essentially a probability, and you get your expected number of successes. Likewise, n times 1 minus p naught is the expected number of failures. So once we check that out, we have to have expected number of successes, expected number of failures to both exceed 10 in the problem. If that's correct, then we have a large enough sample size to proceed and be confident that the p-value we get and the conclusion we write is an accurate one. So next thing we calculate is the z-test statistic. We did this in section, I believe it was 10.3 and 10.4, we did p-values. But this is also, again, always worth mentioning. When you calculate the standard error p-hat, these values here come directly out of the null hypothesis. We're not using the sample data to check the conditions, nor to calculate the test statistic, the standard error portion specifically. Then after all of that, we're just about there. We take the sample's number of successes, find out just how far away it is from the null hypothesis value. And this is going to crank out the number of standard deviations your data is away from the null hypothesis statement down below. If that's a lot of standard deviations, we're probably rejecting that statement. But if it's small, like maybe 0.2 or something like that, we'll fail to reject it. So after getting through all that, here's the big thing. The p-value of the test is split into 3 different cases. It all depends on what your alternative hypothesis is. Our author always writes direct equality on the null hypothesis. But on the alternative hypothesis, if you see greater than, you're dealing with a right tail test. And this is also telling us exactly where to get the area. Let me kind of fix the spacing here. For a quick picture, it should look something about like this. Having a large enough sample size is ensuring our statistic comes from a distribution that is going to be normal enough in shape. So we'll assume those conditions are true and attempt to draw a normal curve. Not a great one, but that'll do. All of these are centered directly at 0, and that's a consequence of what z is doing. It's standardizing the normal distribution to have a mean directly of 0. So here's mu of 0, mu equals 0, and a standard deviation of sigma exactly 1. The reason it's 0 is we subtracted off the mean from p hat, and the reason standard deviation is 1 is because we've divided by the standard deviation. That rescales everything to here, standard normal distribution. So the next thing we'll do is to get the p-value, because it's a right tail test, we go here and shade to the right. So really what it looks like is just an ordinary normal distribution kind of problem. The statement here verbally says, the area under the z curve, what they're referring to is this right here, the standard normal distribution. Another name for it is just the z curve. To the right of the calculated value of the test statistic, referring to z when they say all that, is your p-value. So the last thing that goes on this diagram is your test statistic z. And then we can put in the standard inputs. This is input 1. Your test statistic goes in first for a right-tailed test. Input number 2 is going to be 10 power 99. And those are the last 2 inputs, 3 and 4 coming from there. So confidence intervals are nice because it's easy to state the formula. By hypothesis testing, it's not terrible to state the formula until you get to the p-value, because there's 3 different cases we have to specify. Any questions at all, folks, with the right-tailed test? Yeah.
That like z value that you're talking about is the same one that is at the top in that equation, right?
Exactly, absolutely. Same z-test statistic. In fact, let's give that an official color on this. I think the test statistic is the trickier part of these notes. So let's put this one in the purple to make it stand out. So whatever your z-test statistic is, that's a tongue-tied word, it'll calculate the area to the right of it if you're doing a right-tailed test. Other questions so far? Okay, The left tail test, you can probably already imagine the diagram, but let's put it on there so it's just officially there. And it gives us a place to look back on the notes if we have to see it again. So for the left tail test, just put down a really fast normal curve. Well, this one's not great, but that'll work. It's centered at 0. Mu is 0, sigma equals 1. So essentially the same diagram, except that, well, we can put z anywhere we would like, but for this kind of a hypothesis, we'd usually assume that z is somewhere out here. We would hope it's really far to the left, because then we're rejecting the null hypothesis. But it could be really anywhere. Let's put it here officially. This would be a picture where we failed to reject the null hypothesis. The p-value is close to 50% this time, or 0.50. Let me keep the shading the same. Oh, geez. So let me fix this real quick. I think we need a new normal curve anyway. Let's do a do-over on that. It's a little bit of an improvement. So I wanted to put a border that goes up here to match what we did before, and we shaded in black. It's kind of low effort shading, but there it is. The highlighted region right here is your p-value. In the calculator, you would put in input number 1, negative 10 power 99. Input number 2 is your test statistic z once again. Let me point at that a little bit better. And last 2 inputs. So those are the standard kind of tests that we've done. Now you might have noticed when we walk through the notes, say starting around section 10.3, 10.4, we never really did the two-tail test. Not because it's terrible, but it's a little bit more involved to explain. We were just doing these two just to warm up. So the two-tailed test implies we're going to get a p-value from both tails of the normal curve. But there's also symmetry that we're dealing with. So for example, if I had a z here, and I place another value right over here, call that, say, negative z. I'll correct the diagram in just a moment. If this one was a two-tailed test, there would have to be a not equals there, and then we would just take both of these areas. We would just double it. So that's the meaning of a two-tailed test. But for the sake of actually writing out what this looks like so we can organize for the calculator, I think it's a good idea for us to break this into 2 different situations. We'll do one where z is positive, and one where your test statistic comes out negative. So we can just divide it into those 2 different cases. We'll double the area, but if it comes out as a positive, here's what the picture would look like in this case. Sorry, it took me a moment to get that on there. Okay, so we've got a positive z. That means it's going to be somewhere, say, over here. So z is positive. In this diagram, then we'll take this area right here and double it. So let's write down an actual statement. This time the p-value is going to be equal to 2 times probability that z, let's call this a uppercase. Let's actually go with x. We're usually writing an x right there. Probability that x is bigger than whatever our z test statistic came out as. So that would be the probability statement. And this one is very tricky in the calculator. Well, it's not tricky in the calculator exactly. It's okay to put in probability x bigger than z, but the trickiness of it is that 2, the fact that we're doubling this area right here, is really, really easy to miss. So that's if z is positive. If z is negative, then the picture for this process probably looks a little bit more like this. So the moment we asserted z is negative, it's got to be somewhere over here to the left. We can place it, say, right here. We accumulate area to the left of this location. But we would also accumulate area to the right of that location. That's why it's a two-tailed test. But by symmetry, we just have to double that, and that would be the correct answer. So we don't have to necessarily find area in both tails. That area up here is exactly the same as this one. So the probability statement this time would be the p-value is equal to 2 times probability that x is less than z. And that 2 definitely deserves highlighting again because it's easy to miss on what's going on here. Let's actually shade in yellow right here. I think I kind of like that idea. Just to remind us, we're doubling that area, so we are getting area effectively in both tails. So finally, that's the full specification of the procedure. The p-value is not as bad as it looks, but it feels like there's a lot of stuff going on because of all these different descriptions, depending on your alternative hypothesis. But that was the purpose of section 6.5. If we get a lot of practice on the normal model, all these things become a little bit more easy to get through. Well, after getting through the p-values, the next thing is a real quick reminder that once we go and make a conclusion, there is only 2 possible conclusions really. They're all going to be dependent on the significance level alpha. Let's highlight that in purple again. And the work goes, if your p-value is small, meaning less than alpha, this is the good case. Let me make sure that's readable. This is the good situation. We found evidence that the alternative hypothesis is true. But if your p-value is ever greater than or equal to alpha, here we'll say we failed to reject the null hypothesis, meaning we failed to find evidence that the alternative hypothesis was actually true. So notice we're either going to say we found significant evidence, or we'll say we failed to find significant evidence, both talking about the alternative hypothesis both times. So those are the only 2 conclusions. They'll come from the significance level alpha, and occasionally some of the problems will ask you to choose one. You can overthink this if you want. If this problem is really interesting, you can break it up and decide what is a type 1 error, what is a type 2 error. We did that in section 10.2. And then you can decide what is a sensible value for alpha. But I also would say analyzing type 1, type 2 errors is a huge problem already on its own. And alpha equals 0.05 is okay as a default. It's a compromise between type 1, type 2 error. And if you just throw a 0.05 on, let's say, example number 1, that would be okay. Well, I think we're about ready to start working on example 1. Any questions before we start this one? Okay, so it says, the Substance Abuse and Mental Health Services Administration conducts a survey on drug use by type of drug and age group. So they are interested in the drug groups and the drug and the demographics that take that drug. They published results in the National Household Survey on Drug Abuse. So you can Google that if you'd like to get some interesting data for statistics problems. And according to that publication, 13.6% of 18 to 25-year-olds were current users of marijuana or hashish in the year 2000. For this right here, current users of marijuana or hashish, let's just paraphrase that to just saying THC. I think that's a decent paraphrase on this problem. Then it goes off to say, well, this was from a year 2000 study. They found 13.6% are users of THC. And now it says a recent poll. Curiously, there's no date on that, but let's just imagine it was 2023. This is the portion where the problem is now made up. None of this data is real, but makes for a great statistical problem still. So a recent poll of 1,283 randomly selected 18 to 25-year-olds reveals 205 currently use marijuana or hashish, current THC users might say. Then they say, do the data provide sufficient evidence to conclude that the percentage of 18 to 25-year-olds who currently use marijuana or hashish has changed since year 2000? I'm highlighting this sentence here this time. Let's go with just gray. Because anytime you see a question in a problem like this, that's probably the alternative hypothesis. This is the actual research question they're interested in. So we were probably going to reformulate that into an alternative. But first, we have to read through all this data again and see if we can pick out any values. There's definitely a sample size. Anyone spot how large the sample size is on this one? Exactly, we've got 1, 2, 8, 3. Then after we get a sample size, next thing we would want is number of successes. Now this time it's not for checking conditions, this is just to get the statistic out. The number of successes is given right here. The 205 current users of marijuana or hashish. Keep in mind, it's not a success in the normal sense that that's a good outcome. It's just a success. That's what they were interested in this study. So number of successes will be 205. And the next thing we need is, let's turn up just for a moment and look at our notation. The next object we have to find is the thing that's been highlighted here in blue. The P0 value is going to be critical in getting through the hypothesis test. We need it just to state the null hypothesis and really to do everything else, including condition checking. So because that value is used really everywhere, this step becomes very, very important. Guess we'll go for blue on this. We need to find the hypothesized value P0 or P sub 0. Anyone spot where P sub 0 is on this problem? Or what the quantity is? Oh, that's okay. It wouldn't be the 1283. It's going to be a value that's going to be our best guess of the unknown parameter or unknown population characteristic in the study. Exactly. That's this quantity right up there. Thanks for specifying that. So the moment we see this, we've got a hypothesized value. This was from the year 2000 data. The population of 18 to 25-year-olds said about 13.6% were current users of THC. But now we're dealing with a recent poll, so we're wondering, did the population change? Has the value, well, that's literally what they said. Has it changed? Has it gone up or has it gone down? So after that, I think we're ready to delve into the problem. I keep on forgetting to do this one little thing. Sorry for the distraction on there. When it says parameter, our author does use that here and there, but she uses more often this statement, population characteristic. I'm trying to get in the habit of putting down the notes, but a few of them just keep on slipping by. Let me put this in red. Let's just say here, or parameter, just to mention, we're really saying the same thing, either way you say it. So we need to define our unknown parameter. It'll be the true proportion of all, and pretty much this is how all those statements are going to start. We have to say proportion right here because we're indicating P for the population characteristic. I said of all just to emphasize we're dealing with the population now, we're describing it. Then if we look up what a success was, that's a good hint on filling out the rest. There was 205 successes, and that was the 18 to 25-year-olds being current users of marijuana or hashish. So let's say here, it's the true proportion of all 18 to 25-year-olds that are current, let's go with THC users. I'm assuming that's correct if you say marijuana or hashish, whatever that is. So current THC users. Now, once we have our parameter P down, first, does that look all right to folks? Any additions or changes you would want to make to it? Okay, once we have that, here's the next step. We state a null hypothesis, and it's a statement about the parameter we just wrote down. We'll say P is equal to, and over here, I did make a weird mistake. 13.6 looked okay, but it would need a percent symbol to be correct. But that's probably not the best way to state that, really. Let me fix this right here. If they give it to you as a percentage, we need to change that and really make it a decimal. So it should be a 0.136, really, right here. And that was after saying that's the most important number in this whole problem. So don't make a mistake like I did. Definitely convert it down to a true proportion. So 0.136 would go right exactly here. Let's keep on highlighting that thing in yellow because, again, that value is going to be everywhere in this problem. Here's our null hypothesis. The alternative hypothesis, HA, is also a statement about P, and it also compares it against 0.136. And this is the pivotal part of the problem. We have to decide on one of three different tests. It's either going to be a left-tail test, or putting on the wrong thing, or a right-tail test, or it's a two-tail test. The context has to supply us with information if it's right-tailed. Somewhere they have to tell us that's what they're looking for. Or if it's a left-tail test, the context has to indicate that. And if there's nothing there that's pointing you in one direction or another, this one is still the default. Default test. Even on an exam, if it was, say, a right-tailed test, but we did the default test, we might lose a very minimal amount of points. There are some people with their really strong opinion in statistics who say this should be the only test that we use. They have really strong opinions, so we can't take their opinions for as fact on every problem. We'll always have to do what the context indicates. If they want a left-tailed test, we'll do one. If they want a right-tailed test, we'll do one. But anyone spot what the real test should be for this problem? Two-tailed? I agree. We have to find something that indicates that. So let's put in first the not equals right here. Then anyone see the word that's here in the gray that would indicate a two-tailed test for not equals? Good eye, right here. That's all they have to say to direct us immediately to a two-tailed test. If they said has increased, we would have put a greater than sign there, or if they said has decreased, we'd have done a less than sign. But they're testing for any change whatsoever. Now at this stage, the procedure is still not complete. We can't do a hypothesis test unless we know what we're testing. You have to indicate the parameter, then you state the null, the alternative, and there's still one last thing. We have to choose a level of significance on this problem. Again, that can be a pretty tough thing to do. If you set alpha equals 0.05, that would work out on these kind of questions. But if folks would want, we can do a careful consideration of what type 1, type 2 error would look like in this situation, and then select our significance level alpha. Well, any volunteers? Should we go with a 0.05, or does someone have a different alpha that you would like to use? Maybe another question. We could analyze type 1, type 2 error on this problem and help us choose which one we should use. But if we did do that, keep in mind, you're never, ever expected to do that on a real exam. That takes too much time. That's a whole different question all on its own. So I'll leave it up to the class. If we do type 1, type 2 error, we'll probably come back to the full procedure on Wednesday, or we could just put an alpha at 0.05. Any volunteers for one way to go or the other? How about a 0.05? Looks like we're kind of on the fence. And 0.05 is also kind of on the fence. And it gives a pretty good compromise. I think I did look at type 1, type 2 error on this problem. And I honestly didn't feel like one was necessarily way worse than the other. If I was going to do this, I probably would have set alpha at 0.01 personally. That way, we're only going to make a strong conclusion we found evidence. At a higher level of evidence would be required. So I would make it really hard to reject the null hypothesis before we put out any new information, dropping that to a 0.01. But these kind of problems are pretty strange. When it says choose a level of significance, it's really up to you. Not every problem will ask this, but it can happen on a quiz and even on the final exam. So if you put in a 0.05, that's okay. If you're thinking about type 1, type 2 error, and you swing this to a 0.01 or 0.10, that's also okay. But once you settle on a value, we are now fixed. Our p-value is going to be decided on whether we reject or fail, all hinging on alpha now. So next thing we'll take a look at is if the conditions are even met. Let's take a look here. It said 1,283 randomly selected 18 to 25-year-olds. That's great information right there. So we can say these data were randomly selected. The trouble, though, is all they said was they were randomly selected. We don't know how they randomly selected them. We're going to have to trust that this was a simple random sample or something equally rigorous in their random selection. It wasn't, say, like a convenience sample where maybe people randomly walked into a school and they were just interviewed. That would be very tainted, compromised, biased data in that case. But that's not something we can directly assess unless they tell us their methods. So instead, we're going to address the sample size. Here, we are not looking at the actual number of successes 205. We're thinking if the data wasn't even collected, but we knew we were going for 1,283, and if we assume the null hypothesis is true, we want to know how many successes do we expect. So we can write expected successes is going to be equal to the sample size multiplied by the hypothesized value P naught. So it comes into play again right here. This will turn into 1,283. Take 1 minus the 0.136. And now we need a calculator. I forgot I need a calculator. Let me grab one real quick here. So 1,283. Oh, sorry, I must have been thinking of the next line. I put in a strange value here. This should have been 0.136 like this. I think I was thinking of the second equation down below where we go 1 minus it. I'm not sure why I jumped the gun on that. That would have been expected number of failures, not successes. Apologies to everyone working in pen so far today. Should have been just this value, and it comes in as, oh, that just looks weird. Let's fix that. 0.136 goes here. Now multiply through with the better looking numbers. We get 1,283 times 0.136. And it'll come out as 174.488. We can round this to say 174.5. It's kind of weird rounding to a decimal, but these things are typically decimal answers when you see these. Then after we have expected successes, we can calculate the expected failures. There is a formula. It's going to be the one I almost accidentally wrote in here, 1,283 times 1 minus 0.36. But honestly, the fastest way to get it is just take the sample size again, 1,283. Take what you already calculated, the expected successes, 174.5, and you'll get the same exact value. So no reason to work extra hard. Let's just treat ourselves to a fast computation. 1,283. On your calculator, you can even go minus, up arrow, and you don't even have to type in that number. Let's round this to 1108.5. So our benchmark for our sample size being large enough, in our textbook, it's going to be at least 10 successes and at least 10 failures. And that's going to be true whether it's a hypothesis test or a confidence interval. So that at least matches up with section 9.3 and 10.5. All we have to say now is, since these are both greater than or equal to 10, we can put here, that's definitely greater than or equal to 10, and so is this quantity. The sample size is large enough. And that would mean, finally, here's our overall conclusion on all of this work here. The conditions are met. So now that we met the conditions, we can have really great confidence that the conclusion we give in part E is the right one. If our conditions weren't met, we didn't have a whole lot of those. It did happen on a quiz, but if they're not met, I'd probably still make the same conclusion, but I would say later on after I write it, however, these results cannot be trusted because the sample size wasn't large enough. We probably have inaccuracies in our statement. But here it looks like everything is working out great. And now we're doing the so-called test statistic. This is kind of how we're used to seeing our problems. They ask us for things like sample proportion of successes or standard error. This one's just directly asking for a test statistic right away. But it's a vocabulary question. We just have to know that when you see that, it's referring to Z equals P hat minus P naught and divide that whole thing by the standard error of P hat. So to calculate this test statistic, it'll be all about that. This question is a little bit tricky though, because there's really kind of two things we have to calculate. We should calculate P hat first just to start this off. I'm sensing the need for a little bit more space, so let's drop this down. And for calculating P hat, we have to return to some of the information we summarized. So let's take this. Here's how the computation will start. First for P hat, it's going to be the number of successes in the study, 205 THC users divided by your sample size, 1283. We've calculated that one a lot, but it's always good to still be careful with these things. So 205 divided by 1283. This results in 0.1597. We're asked to round to 4 decimal places. But this question's a little bit different. We're doing multiple things all rolled into one. If I saw a question here where it's asking for 4 decimal places, I would typically assume the final answer, Z itself, is to be rounded to 4 decimal places. Let's keep 5 places for extra accuracy. 0.15978. If you kept just 4 places rounded to 0.1598, that's always going to be totally fine on a quiz or exam situation. Only reason I'm keeping 5 places is WebAssign can be a little bit nasty sometimes with rounding. A little bit of extra precision on your intermediate computations is never a bad idea. Then once we have that, we can now say Z is equal to, at the moment, put in the P hat value, 0.15978. And we can even put in P naught. P naught was the 0.136. Last thing we need to get our valid test statistic Z is we just need to crank out the standard error right down below here. I think we usually use green for that. I think we have an extra color available to us. Let's use green again. Any questions first, folks, before we go for the denominator now? Okay, well, now grabbing the standard error by formula, we're doing standard error of P hat. It's going to be square root of first P naught times 1 minus P naught. Never seem to make those big enough. Let me extend that out. Then divide by your sample size n. Yeah, go ahead. I'm glad you asked that. If we were doing, say, a procedure over here at the 9.3 right here, let me pull that up, then our standard error is exactly what you said. We have to have a P hat there. And that's in red because I think I made a typo on the notes. We had to fix this after the fact, after showing it to the class. But if we go to a hypothesis test, this one's really weird. We're checking the hypothesis by completing the standard error using the value P naught directly from the null hypothesis in this case. And to me, this is the worst thing about doing a confidence interval hypothesis test right after. By muscle memory, we feel P hat should go there, but we're putting in something different in this case. Other questions about that so far? So it suddenly becomes like the null hypothesis is the most important thing you would write down when doing this, because the value P naught is everywhere, including the condition checking. Then down in standard error, we have to throw it down here as well. But after we put in the value, it's just going to be like a normal computation. So here's P naught, 1 minus P naught. We'll start by putting in about 0.136. 1 minus 0.136. So that's where the hypothesized value went, both here and here. Then finally, do a division by sample size, which was 1283. So that's what it should look like right before throwing it into the calculator. Other questions so far, folks, to that stage? Okay, I think we've done probably about 30 of these at this point. They just show up so often. But it's another problem, just like p-hat, where always good to go carefully on this thing. So I'll hit second power 2 button to call that square root. That way, no way I'm going to forget it now. That's the first key to hit. 0.136, parenthesis, 0.136. Oh, I made a mistake. There's got to be a 1 minus first. What I'm attempting to do is just read that out verbatim. 1 minus 0.136. Then close that parenthesis, divide the whole thing by 1283. And we should have it. Double check that this bar is extending all the way through, including the denominator, or else that would definitely influence our results by quite a lot. Here's the value we get altogether. To 5 decimal places, we can record 0.00957. I think at this stage, we could probably move that down. We still don't have the test statistic Z. We were putting it together piecemeal. Here's P hat, hypothesized value P naught. And finally, here's the standard error, 0.00957. If the null hypothesis is true, this is the exact standard deviation of the sampling distribution of P hat. But if it's false, we're going to detect this as not compatible with our data once we calculate our Z test statistic. So let's finally figure out how many standard deviations we are away. When we say that again, the reminder is we're trying to find how many standard deviations we're away from 0.136 when we calculated 0.15978. This is saying about 16% are THC users. The null hypothesis was saying about 13.6, so that's significantly different. However, that's never the full story. We want to know how different in terms of standard deviations. So that denominator becomes like the most important thing in a test statistic. So let's calculate 0.15978 minus 0.136 from the null hypothesis, division by 0.00957, finally gives us this result. Now this one I'll round to the official 4 decimal places that they wanted, 2.4848 altogether. But once you're looking at 2.4848, that's about 2.5 standard deviations. That is pretty far away. At this stage, you could almost say the null hypothesis is probably false. Getting a value 2.5 standard deviations away from the center is a rare event. But now we have to quantify exactly how rare that is. And that's where we return to the p-value. This one's a 2-tailed test, so it's a little bit tricky. We're not going to try to rush through it in a minute, so I think this is a good stopping point for us. Sorry we didn't get too far on this problem, but so far, this is all the work that we've done from section 10.1 through 10.3. The p-value we did at 10.4, now we're just doing it officially with the formulas that we have up above. Well, that's all I have for class today, folks. Any questions or comments before we call it a night? Okay, well, have a great night, everyone. When we come back, this is where we'll be. And I should have our 3rd exam also graded and returned on our Wednesday's class as well.